clouds coming in.
Yep.
Yeah.
Slide in the last second.
Yeah. What's your plan for the? You said you're probably not be like responding.
There's seats up here. People need seats. I'm sitting there. Okay. Everyone come in and have a seat, please. Welcome to the last CFA colloquium of the fall. It's my pleasure to introduce Anna Bonazza. She is a member of the ITC, is an ITC postdoctoral fellow here. Anna received her PhD from Yale in 2016. And she is an expert in the field of galactic archaeology, which we will hear a lot about over the next hour. She has made a number of important discoveries in her career. She was one of the first to identify the so-called field of streams of debris in the stellar halo of our galaxy. She identified a new stream called triangulum as a graduate student. And recently, she's been working to use these streams to study the nature of cold dark matter. So we'll hear a lot about that today. Anna is somewhat unique in both being a theorist and an observer. She knows how to go to telescopes and take data and also run simulations and work with actual equations. So that's a somewhat rare occurrence these days. Actual equations. She's also done work as a grad student in astroseismology, so she has very broad interests. So let's join me in welcoming Anna here today.
Thank you. Thank you for being here in such a huge number at the very last day of the CFA colloquium. So I'll try to keep it festive, and I want to start with a beautiful image of the Milky Way because I think it really depicts why I love working in this field. And at least part of the beauty is because this is the end result of billions of years of cosmological structure formation, and for studying the lethal properties, motions, chemical abundances of stars, we can ask really big questions about the universe itself. And so everything I'm going to be talking about today kind of neatly falls into these two big questions. Where do we come from, and what is the universe made of? And so these are very broad, and people come from them from very different directions. And one of the great pleasures of being here at the CFA is that many of my colleagues are answering these same questions. So for example, the extragalactic group might think of this sort of question, where do we come from, to just understand how the initial blobby clumps of gas observed at hydrogen shift form into this distribution of galaxies we see at the present. Much more closer to home, planetary astronomers might think that where do we come from really means from how do we form planetary systems that we observe in great numbers today from the protoplanetary disk that we also observe now in great numbers. And so the scale that I will be talking at will be somewhere in the middle. So you'll be on this Milky Way scale of an individual galaxy where we do resolve individual stars. And as for the specific question I want to answer here, I provide this quote from the review from Ken Freeman and Josh Blunt-Horta, and now it's almost 20 years old. And they sort of define the field of galactic archaeology here, saying that we can now study, and really the now is the now, not the now in 2002, is that we can study the fossil remnants of the early days of the galaxy and then associate different components to their initial birth clouds. And how do we do that? Now, the revolution now is really has been brought by the Gaia mission. And here is the view of the night sky from the Gaia that we already have seen through, even in this series, several times. And what the Gaia brought us, it was not just like the positions and colors of almost 2 billion stars, but also their proper motions. And so this is a visualization that was created by 2 graduate students here, Josh Spiegel and Katrin Zucker, who had taken several million of those stars, reran basically all of the Gaia information we have on them with additional 11 bands of photometry to provide better distances to those stars, and showed how they move on the sky. So here are the lines that tracing the average motions of stars in that direction on the galaxy. And so you can see that closer to the galactic plane, stars are actually moving in the plane, which is what we would expect if it is indeed a rotating disk, that is. Out of the plane, the motion is more random, and those are this is the signature we would expect if those are stars part of the halo. Those kind of more accreted over here. However, you might find something conspicuous in this dichotomy, in that there is some ordered motion in the halo itself, and it is like following this track over here. And that, turns out, is one of the most recent accretion events onto the Milky Way galaxy, the so-called Sagittarius stream that points over where the Sagittarius dwarf galaxy is hiding kind of behind the galactic disk. And so the really neat thing about this whole goal of galactic archaeology, of finding, asking the question where stars were born, is that we can now just look it up. We can like check the stars and see like where they have been moving. So this has been like a great effort from Josh and Katrin that only use basically 5D information. So it's just projected motion in the plane of the sky and knowing the distance to the stars and of course position on the sky. However, we can do more if we have the 6D information, including the radial velocity data. And so here is one view of the very inner circle, stars closest to the sun, where it's easiest to measure the full 3D positions and 3D velocities. And what I'm showing on the x-axis is the velocity in the direction of the rotation. So the sun would be sitting around here, moving at a velocity of 220 kilometers a second. And on the y-axis is the perpendicular component of the velocity vector. And so in this space, all of the stars are here close to the sun, and all of the halo stars would be those that are moving at some larger velocity with respect to this kind of galactic rotation. And one of the surprises we found 2 years ago is that when we looked in more detail in all of these halo stars, we saw that there is a range of metallicity. So the color coding here is for the stars that have spectra that are good enough to measure the metallicity. And we see that there are like some that are fairly metal poor, but there is a number of them that is metal rich, even more metal rich than minus 0.5 dex in iron. And that was surprising because we expected some of the stars, or we saw previously evidence of accretion, and those are supposed to be low mass events that have low metallicity. And yet here we have a population of high metallicity stars moving on halo-like orbits. And so we were a little bit puzzled of what is happening there. But luckily, this improvement in the quality of the data we are getting has been matched by the quality of the simulations of the Milky Way that people are running. So what we then set out to do is perform this exact same experiment in a simulated Milky Way-like galaxy. So on top is one observed galaxy, sort of like the Milky Way, and here is a simulated Milky Way galaxy from the FIRE team, particularly their like the M12I model. So what we did is go to a solar neighborhood in the simulation, draw like this same circle that encompasses our observed data in the Milky Way, and make the same diagram as we saw before. And so as in the observed Milky Way, So where most of the stars are in the disk, in the simulation, most of the stars are in the disk as well. However, there are a number of stars in the halo orbits in the simulation as well, and a lot of them are metal-rich, like we see in the galaxy. And so the benefit of, well, this is very encouraging that, well, on both ends, that the simulators are getting a lot of these detailed properties of kinematics of stars in the solar neighborhood correctly as we observe in the Milky Way, but also provided us an opportunity to see where those stars came from. And so if we plot the formation distance as a function of star particles in the simulation, so this is distance from the Milky Way host galaxy, as a function of age or time, and these are just stars that end up on halo-like orbits. We see that some stars are born very far away, and those are kind of continue being formed here, and we think those are stars being formed in dwarf galaxies that are being accreted to the Milky Way host. However, a number of them forms very close, even within an inner kiloparsec from the host galaxy, and yet at the present day, they end up at this 8 kiloparsecs away from the galactic center. So we really here see that there are actually two ways to place stars on halo-like orbits. They can be either accreted from a dwarf galaxy, or they can be formed in situ, but then kicked out of the disk or that protogalactic disk out on the orbits that lead them to pass through the solar neighborhood at the present. And so this has all been enabled by actually having the 6D phase space information for those stars. And we kind of got greedy. I wanted to do more. And so here at the CFA, Charlie has been leading, and I've been a science co-lead of the H3 survey, which stands for hectashell in the halo at high resolution. And this is a blind spectroscopic survey between 16 and 18 magnitude, really tailored on MMT with hectashell, and really tailored to target faint stars that won't have radial velocities or spectra from the Gaia mission. And there has been, so the survey is halfway done. We have 100,000 spectra already. And there have been a splash of papers. There's been a survey paper earlier this summer. Then Phil Cargyle, who is a postdoc here and leading the derivation of stellar parameters from the spectra, has a paper showing how we do that and how we can derive accurate stellar parameters from combined spectra and photometry, even if our signal to noise is only 2. And then we had already 2 interesting discoveries from the survey itself. Charlie showed that on average, the halo is metal-rich throughout the galaxy with very little variation out to 100 kiloparsecs. And then Dennis Risky from Arizona has shown that based on the kinematics of stars in the very outer parts of the halo, we can place a very stringent lower limit on the mass of the Milky Way to be almost 10 to the 12 solar masses. So this is something that's been already published, and but what I want to talk to you more about today is some stuff that is already in the works still. And a lot of it has to do with finding structure in this, identifying progenitors of the Milky Way in this new data. And we expect the progenitors of the Milky Way, like the small dwarf galaxies that are coming in, to be continually losing stars, tidally disrupting. And so as time goes on, it becomes harder and harder to disentangle different progenitors of the Milky Way if we just have a sample of halo stars, or if they were not colored here. However, if we are able to calculate energy and angular momentum for these stars, we can see that there is a lot more regularity here. And it is because to the first approximation, our galaxy is sort of spherically symmetric and not changing in time. So both the energy and angular momentum should be conserved. And so if we can calculate these quantities, stars originating from the same progenitor should be also localized in this plane. And to do that, we need a 3D velocity and 3D position to calculate the angular momentum, and to calculate the energy, we, in addition, need to assume something about the gravitational potential. However, that's exciting because that's exactly what we have now with the H3 survey. And I want to highlight some of the work that graduate student Rohan Naidu has been doing along those ends. So I'm showing here giant stars observed by the H3 survey in galactic coordinates. So the sun would be over here, offset at 8 kiloparsecs in the galactic plane. And here is the energy and angular momentum. As you can already see that this this diagram is not uniform. There are some clumps over here, and they correspond to structures that have been previously discovered and discussed in the literature. So Rohan made a very careful selection to tag them, and so this most massive event is the so-called Gaia Enceladus. This lower mass over here is the Sagittarius, the same one that you saw in the movie at the very beginning. And even in this position space, you can see it's somewhat more coherent than other structures. Then the next one in mass is a so-called Sequoia event that was discovered by our very own Qichul Myong. And this over here is the Helmi stream that was discovered way back in '99, and it actually started this whole idea of being able to find progenitors of the Milky Way in this space. And so Rohan is, among his many other projects, finishing up this paper, characterizing these known structures that we see in the H3 survey. But what I think is even more exciting is that when you subtract all of these known ones, you are still left with more overdensities. So this might be less massive accretion events on the Milky Way, which I think will be very interesting probes of the early galaxy. The reason why I'm collaborating with Rohan is because I'm interested in seeing what are the chemical abundances of those early galaxies. And we can measure them at a much higher precision than we can do directly at early redshifts. So here is, just provide a little taste of this, here is the diagram of alpha over Fe abundances versus Fe over H for stars in the survey. And we see some trends over here that correspond to the thin disk, the thick disk, and the halo. And so I thought it was interesting to overplot stars that Rohan identified. They are all in this halo cloud, and even though their mean metallicity is different, I thought it was interesting that they're all following this similar trend in the buildup of iron abundances, which might be telling us something about the time scale for star formation in these galaxies. Of course, we can turn this around and analyze just this space itself. And just to leave you with a little bit of teaser, here is the figure again, color-coded now by age. And so you can see some things that we expect, like we kind of know from Astronomy 101 that the thin disk is younger than the thick disk. But it was really interesting for us to see that there might be some substructure even within the thin disk that wasn't initially at all what we were set out to do with this survey. We are finding now interesting substructure like within thin disk itself, and those stars actually do appear to be on disk-like orbits. So it's we're still working on understanding whether those are some structure within the formed in a disk, or actually something accreted in this very planar orbit. So to wrap up this first part of where do we come from, we are now really able to identify stars in the Milky Way that have come from different galaxies. And also those that have been formed in the Milky Way itself, but that have been kicked on different orbits. And as we go further in, I believe, very near term, in the next 5 years or so, we will be able to build a complete census of all of the progenitors of the Milky Way galaxy and then really study in detail the properties of star formation through cosmic times. And what I want to transition into next is that finding substructures that have been accreted from dwarf galaxies onto the Milky Way, they tell us something about the history of the galaxy, but they also have been orbiting the Milky Way itself and can tell us something about the galaxy at the present. And so this will fall under this umbrella of what is the universe made of? And we know on cosmological scales from the CMB and the large scale structure properties that 85% of the matter in the universe is dark. We don't know what this dark matter is. There are several candidates and theories that make predictions or differing predictions on this Milky Way sort of scales. And this is what prompted Mike Boyle and Colchin and James Bullock in a more recent annual reviews of astrophysics contribution to state that the search for abundant dark matter halos with inferred virial masses substantially lower than the expected threshold of galaxy formation is the most urgent calling. And the reason they say that is because our most prevalent cosmology, the lambda CDM, really says that these low mass dark matter only subhalos should be very abundant orbiting the galaxy itself. Other theories, like warm dark matter or fuzzy dark matter, predict that there should be none. So the goal for this second part of the talk is to constrain the clumpiness in the Milky Way halo to say whether there actually are any of these predicted low mass dark matter clumps. And the way we transitioned this into some smaller scales, there's a number of our colleagues in the physics department that have different theories of dark matter that some of them can interact with our universe, or like the baryons, some can self-interact, some can annihilate. And so pinning down like this nature of dark matter on the Milky Way sort of galactic scales would actually also inform the theories of the particle nature of dark matter. And the reason we can do this is that these streams that I've been showing so far can be very thin and thus sensitive tracers of matter density. So you saw in the movie that the more massive structure formed a thicker stream. As we go down to lower mass events, they become thinner and thinner. And here I'm showing a tidally disrupted globular cluster that has been evolved in a smooth galaxy, something like predicted in a warm dark matter universe. And what we expect to see, if this is the case, would be a very regular looking, thin, unperturbed stream with almost constant density along as we go along the stream. However, if we put the same globular cluster on the same orbit in a cosmological dark matter halo where the dark matter is cold, and there are a lot of subhalos orbiting around the galaxy and interacting with this stream as it is disrupting, we expect to see something like this. So the general shape is still the same, but there is a lot more structure here. So there are variations in the width and in density along the stream. There are some gaps here. There are some parts of the stream that look almost detached and stars kicked out of the stream itself. So this is, there are other ways of looking for signatures of small dark matter clumps in galaxies. However, this turns out to be the most sensitive one. And through these perturbations, we are hoping to really find we think we can detect subhalos down to 10 to the 5 solar masses. The measurement is not easy. So here is our view of stellar streams in the North Galactic Cap. So you're seeing it now for the third time. So the most massive thing is the Sagittarius stream, very wide, a disrupted dwarf galaxy. Less massive event is over here called the orphan stream. The orphan because we haven't traced it to its progenitor galaxy, but we do think it is a galaxy because it is still somewhat wide, although much lower mass than Sagittarius we expect. And then here in the corner is hiding a Polymer 5 globular cluster that has extended tidal tails. These are much thinner than either of those streams. And those are the, sorry? Yes, also wiggling. This will become important in just a minute. No, that's, you're ahead of the time. So this map was made in 2012. I made it using the SDSS data. So some of these things, as Erin pointed out, are somewhat tentative, that it looks wiggly. But it is streams like this that we will want to study going forward. So thin streams like Polymer 5, and if you look carefully, you'll see another thin stream over here called GD1, which we think is also a disrupted globular cluster because it is so thin, but we don't see the progenitor, so we think it's completely disrupted. And so just looking at this, it's kind of hard to make that comparison to say conclusively whether there are any gaps. Like we see, well, this might be a gap, but there's just a lot of variation in the foreground as well. But luckily, in the last really year or so, this really just changed, and it's a completely different picture. So I'll show updates on both the Polymer 5 and the GD1 stream. Starting with Polymer 5, I made a similar map to this one, which is just based on the colors of stars, selecting those that we think are consistent with being main sequence turnoff, that are typically bluer for globular cluster stars than for the majority of the stars in the Milky Way. And so if we do the same exercise, but instead of SDSS, use the legacy surveys with some additional data that I'd taken during my PhD, it turns out that we can now see many features in this Polymer 5 stream to a much higher detail than we were able before. And we're most excited by the fact that those actually look like there are some gaps over here, and that this part of the stream that was actually not observed with SDSS previously is actually becoming wider. So there are some signatures of perturbation, and I didn't even point it out, but Erin pointed out it does look like the stream is wiggling and changing direction as well. So these are clear I think these are clear signs of perturbation because when, so this is work I had done with Sarah Pearson and Adrian Price-Whelan at the Flatiron Institute. And when we simulated disruption of a globular cluster on PAL5's orbit in a static Milky Way, we got something that looks like this. So definitely no gaps, not widening, or not, at least not to this degree. However, we could reproduce many of these features in models that featured a rotating bar at the center of the Milky Way. So we think that Polymer 5 actually may be on a resonant orbit, and that both the gaps and this widening of the stream could be produced by its interaction with the galactic bar. So I think that PAL5, unfortunately, might not be as useful of a stream for testing dark matter, but it is interesting that we can still put constraints or parts of the galaxy that are otherwise really hard to tackle, like the bar. However, GD1 turned out to be a more fruitful stream to look at, and it's mainly because it's orbiting in the opposite direction from everything else in the galaxy. So it's a retrograde stream, and that was crucial because that means that it was really easy to pick out in Gaia proper motions as it was moving, opposite direction from everything else. So here is the distribution of most likely members of the GD1 stream using Gaia data and some Penslar's photometry. As you can see that we were able to actually completely eliminate any contamination from the Milky Way. All of the stars are along this thin line. there are some features here. Again, the gaps that we come to expect as a signature of some perturbation. And most excitingly, or most unexpectedly, there are some stars that appear to be outside of this main body of the stream. And when we had taken, simulated a model, simulated globular cluster disrupting on the orbit of the GD1, we could reproduce one of these gaps by saying that the progenitor used to be here, but it actually just disrupted. So this is why there is a dearth of stars at this location. However, we didn't see any signatures. We don't see another gap, and definitely none of these extra stream stars. So we wanted to then understand whether this could still be a signature of a dark matter interacting with a stream, and went back to some literature data. And here is a catalog of streams that have interacted with a dark matter subhalo from Yoon et al. Paper. And the location of the closest approach of the subhalo is shown with a cross in every panel. And you can see in many of them it is associated with a large gap or underdensity in the stream. But some of them, like this one over here, also shows this stream fold that we identified as the spur in the Milky Way GD1 stream. However, this really was sort of one-off, and maybe you can say like it's over here. So sort of, even though this work came out in 2011, the community adopted the gap as a signature of the perturbation. And there has been just a lot of work, and this is only a partial list of papers that studied how the properties of gaps in stellar streams depend on the encounter velocity, on the impact parameter, on the mass, and they go exactly as you would expect, that the larger gap is caused by more massive objects that come closer or are moving slower. So what we wanted to do then is to see if we can actually find a model of the stream interaction with a compact object like a dark matter subhalo that would have both the gap and the spur of stars coming out of it. And so to kind of give a more pedagogical overview, I wanted to set up a very simple experiment. Like the simplest thing we could still think was realistic enough for this case. So instead of actually simulating the whole stream, we just put stars on an orbit, on a circular orbit, in a spherically symmetric logarithmic halo. So really the simplest thing. So the stream unperturbed would be orbiting in this XY plane. But the perturbed one, which is shown in dark blue, has had a point mass particle go directly into the, like along the z direction, so in the plane of the screen at time 0. It breezes past. And what happens is that stars closest to the encounter receive a velocity kick. And then some stars gain energy and kind of lag behind the unperturbed stars, and some lose and they're going ahead. So I'll just play this one more time. So you can see that this loop that forms opens up a gap in the stream, so this is what I expected. And at times, as the loop processes around the stream, we can only see one side of the loop sticking out of the stream. So if we project this on the sky coordinates, we get this basic signature that we see in the GD1 data. We see the gap and one side of the loop sticking out and the other side hidden behind the stream. So that got us very excited if this actually could be a signature of an impact, that something impacted the GD1 stream. So we then revisited our initial model that was happily orbiting in the smooth Milky Way galaxy, and then just at a time at 500 million years for the present day, we put it on a collision course with a compact object. And so this is a more realistic case. Instead of a loop, there is more of a ring of stars orbiting around the main stream, which then, when we observe at the present, shows both the underdensity of stars where the perturber past, and some stars that are displaced from the mainstream. So observed on the sky coordinates, this is how our model on the bottom compares to the observed stream on the top. So you can see that to a high degree, like at least qualitatively, these two structures agree. So we can produce the gap that is roughly the right, kind of has density contrast, some stars still remaining here, that has the approximately correct width, and also that has some stars exiting this region and being displaced to this spur that is almost a degree away from the mainstream. And I told her already that the impact happened something like half a gigayear ago. Most excitingly, the mass of the perturber in this case was 5 million solar masses. So this is in this cosmologically interesting regime that if indeed this was a dark matter subhalo, this would rule out many of the warm dark matter models already. However, there is a little puzzle over here, and this is the scale or the size of the perturber that we are measuring. So we modeled the perturber with a Hernquist profile and got that we really are preferring very compact objects. So in this case, this 10 parsecs for this mass would be something more of a globular cluster size, and this is something like 5 times more compact than what we would expect naively from lambda CDM subhalos. And so wanted to see, it would be good to know, it would be, of course, very cool if we found a new globular cluster. We checked for the known ones, and they didn't come close enough, so it has to also pass very close to the stream. So here is the impact parameter. So none of them come very close, but it could be an undiscovered globular cluster. But we would actually want to know if we just found a globular cluster or it is indeed a signature of dark matter. And one of the benefits of searching for dark matter subhalos in the Milky Way is that we can hopefully find some other signatures they have on the galaxy, not just on this particular stream. And to do that, it would be kind of nice to predict where the subhalo should be at the present. It definitely should be compact enough so that it should still survive for half a gigayear. So we performed a very basic search where we varied some of these parameters to satisfy the observed morphology so that it produces the right gap and the right length of the spur and its location with respect to the stream, and then checked where the perturber is in those models today. And we got this. So basically, the current data doesn't really constrain the location at all. There are many possible solutions, and the perturber really, based on that, could be anywhere in the sky. However, the model is predictive. So in all of these models, we can see what would be the most useful next observable that could help us constrain the location. And so what we first checked was what would be the relative radial velocity between the mainstream and this spur of stars. And we got, so now color coding by this relative velocity, we see some trends. The scale is plus or minus 5 kilometers a second, so it's we would need something of a high resolution to measure this. But it looks like there are parts of the sky where they're preferring one side or the other side. And so there was, okay, this is obviously our next step. And luckily for us, the CFA maintains probably the only instrument in the world that is on a big enough telescope that can observe stars faint enough. So we're going between 18 and 20 in magnitude. And it has a high resolution to perform this experiment. And that is, again, hectoshell on MMT. So just to kind of show you how it compares to the previous data, here are the locations of the stars with radial velocity from the literature before our project, shown in blue stars. So sky positions on the top panel, and then on the bottom panel, I'm showing the relative radial velocity with respect to what the orbital kind of radial velocity gradient that should be tracing the stream. And so we see that it kind of roughly goes along this line where we think GD1 should lie. But there are several issues. First, we don't really have stars in this upper part of the spur, and we want to measure the relative radial velocity here between the spur and the mainstream. And second is that the error bars here are very large. So the scale here is plus or minus 25 kilometers a second. And all of the models that I was shown in a previous plot were within this gray band. So it has taken some effort, just like trying to build this up. It was not an easy measurement, but the results are very exciting. So I think it was worthwhile. So we observed 8 fields, 4 in the mainstream that are shown in light orange, and 4 in the spur up here. And when we measure the radial velocity, we get a very good agreement with the orbital solution for all of the all of the fields on the mainstream. And then in the spur, we can see that there appears to be very little relative radial velocity. So even if we zoom in so that the scale is just kind of smaller over here, within the uncertainties or the spread that is mostly driven by instrument systematics at this point, we see that we are sort of within 1 kilometer a second in these 2 locations where we have the parallel observations in the mainstream and the spur. And so I'll be curious to talk to our colleagues who do exoplanets and pushing this boundary even like below 1 kilometer a second to especially for these faint stars. But at the moment, let's just go back to our position sample of possible models. So every point here is a possible location of the progenitor, and now just limit to those that satisfy this very low radial velocity offset. So we are now left with this much smaller sample of models, and it looks kind of suspiciously aligned. It's not random on the sky. And by now you have heard about the Sagittarius stream 3 times in this talk. It was always in a different projection, but it strikes yet again. So we know that Sagittarius is a recent accretion event, and it turns out that it actually is somewhere close to this track that we find where the possible perturber of the GD1 should be. So we don't still have very good all sky observations of the Sagittarius stream. So I will overplot the model from Mir and Dirks, who was a grad student here, and Avi Loeb that they put out in 2017. So you can see that the stellar debris matches this track really well. However, we don't think it was the Sagittarius itself that caused this, that interacted with stream, because it doesn't really come close enough when we integrate its orbit back. However, it might have been something associated with Sagittarius that is now on a slightly different orbit. And to kind of test this idea, we also show what is the distribution of dark matter particles associated with this same model. And you can see that this reproduces this track on the sky even better. So this is very exciting because it kind of gives us a possible astrophysical origin of this perturber that we found from the GD1 stream itself. Our localization in the sky is still somewhat poor. I think it would be hard to imagine any follow-up campaigns with this much area to cover in search for the possible perturber, and hopefully be able to distinguish whether it was a globular cluster or something truly dark. But we are getting the first epoch of HST astrometry in February. So we'll sure be measuring the relative proper motion with respect to the Gaia measurements at the moment, and then in 3 years, hopefully get even more precise measurements to narrow down on this location of the possible perturber. And so to bring this to an end, our question of what is the universe made of, or in the context of this talk, we've been asking ourselves, are low mass dark matter only subhalos present in the Milky Way? I think the answer is that we see some tentative, like very exciting evidence for existence of small bodies such as dark matter subhalos and their effect on the stellar streams in the Milky Way. And with a really near-term data, we'll be able to further constrain the location of those perturbers in the sky to test the nature of those objects. And in this final few minutes, I'd want to kind of bring this even closer. So, of course, finding one low mass dark matter subhalo would be very exciting, already rule out some models. On the other hand, the simulations predict that there should be a whole host of subhalos orbiting the galaxy. And I think we really have a good shot at constraining the whole population, or mapping out the whole dark matter halo of the Milky Way in high resolution. And the way to do that would be through studying many streams simultaneously. So I'm showing here, so far I've been showing you how stream changes as it interacts with a small clump of matter. But stellar streams are affected by the whole distribution of matter in the galaxy. So here I'm showing how the locations of stars in a stream and their radial velocities change as we change properties of its dark matter halo or the disk over here. As you can see that there is change, and the parameters I varied were the mass of the disk, the mass of the halo, and the shape of the halo. And that means that if we have some observations along the stream, we can put some constraints on these parameters. And last year, I actually quantified how well we can do given some simple model of the galaxy that really says the dark matter halo is kind of spherical NFW or triaxial NFW profile. And I assume that we have data on 11 streams observed at the kind of present precision achievable today. And on these two panels, I'll be showing the constraints on the total mass of the halo and the total and the flattening along the z-axis in percent. And so individual points show individual streams. So you can see that there is a variety. Some, like GD1, which is very long, should be very useful in constraining to already by themselves better than 10%, both the mass and the shape of the halo. The median of the distribution is shown with this white larger circle. However, if we have 11 streams, we, in principle, could model them simultaneously because they are orbiting the same galaxy. This is hard to do in practice, but for this exercise, it is fairly easy to provide the motivation why we should be doing it. And it is because if we just take any random pair, the worst performing one is performing at better than 50% of the individual streams. If we further add 3 streams to the combination, the best combination is performing at the 1% level. And if we use all of the 11 streams in the sample, we can constrain, or we forecast to constrain the global parameters of the dark matter halo to better than 1%. So this really allows us to kind of go beyond these simple models and build up a more comprehensive solution that we don't just find like individual signatures of subhalos passing through streams, but actually map them out from their cumulative effect on the whole population of stellar streams. And so this is, at the moment, fairly challenging technically, but I think well worth the effort, because we are sort of standing on the cusp of a revolution in the field of this galactic archaeology. So I want to leave you with how I think our field will change in the next 10 years with the arrival of LSST. So here is the view of the sample of stellar streams observed at a depth of the SDSS, something like limiting magnitude of 22. And you can see some of the streams, like with this lighting, not even that well. But you can see there are some streams, streak lines over here. They're all fairly light, so within 20 kiloparsecs from the galaxy. And now, as I play the movie and we increase the limiting magnitude over here, we see this whole beautiful picture unfolding where the nearby streams are observed in much more detail. So you can see all of those fans or gaps or parts hanging out. And we observe streams as far as basically the edge of the galaxy at 150 kiloparsecs. So I think it's a safe prediction that the future will be exciting. And I can't wait to explore what this sample of streams will tell us both about the evolution of the galaxy and the very nature of the universe itself. So I'll take your questions now, and thank you. Yeah, that's a very good question. So at least in lambda CDM, they're fairly diffuse. So there has been a series of papers that has shown that if they come close to the inner parts of the galaxy, they get very efficiently disrupted by the stellar disk. So there have been some claims that basically there should be no dark matter subhalos within the 20 kiloparsec. However, that is now being revised after like we've been seeing some evidence in stellar streams. And it goes in exactly this direction you pointed out, that if there is something just falling in freshly, it could still do some damage before it gets disrupted. Yeah.
One of your first slides, when you showed the comparison between, it was the phase plots with color-coded metallicities. You showed the Milky Way and the simulation. Yes, that one.
This one?
Yes. I would say that in your real data, there's more data points around where they should be and fewer data points in the outer region compared to what the simulation predicts. Is it something physical or is it just a selection effect?
It's a selection effect, yeah. So I did like a very naive selection, and I show part of it here. So this is with the first year of Gaia, where we didn't even have the 60 or radial velocities from Gaia, but they were matched from some ground-based surveys. And the largest overlap was with actually RAVE, which was a southern sky survey. So you can see that like most of the stars are here, kind of below the disk. And this is, and they peter out way before like this 3 kiloparsec limit. And in the simulation, I just like use all of the particles within 3 kiloparsecs. So yeah, I think many of these would be stars in kind of populating this outer parts that we just don't have as many. Yeah.
What do you think you'll be able to infer about the history of dwarf galaxies near the Milky Way as you uncover more and lighter so less bright streams?
You mean their history within the galaxy, or their history like as from the before? Yeah, so that's, I'm very curious about that question. Like one of the reasons, I wanted to check the metallicities. here of the structures that Rohan has identified as progenitors of the accreted dwarf galaxies, because there is a well-defined relation between the average metallicity and the total mass or total luminosity for the dwarfs surviving in the local group, like both around the Milky Way and M31 and just in the local universe. But this mass metallicity relation appears to be, like when you measure it at higher redshifts, people see evolution in it. And so that would be something I would want to measure, the mass metallicity relation for the disrupted dwarf galaxies, to see whether they obey some sort of or how well they agree with measurements directly done at higher redshift. However, with the survey only halfway through, we don't have a very good accounting of what the total mass of these disrupted things is, because they're like all over the sky. So we, yeah, it's going to be a little more challenging to do it. But yeah, that's kind of where I would go with this.
So the G1 perturber, let's say we narrow it down to 5 square degrees on the sky or something amazing like that. And then we look there, we don't see a Gaia cluster, then what's next? Do we do deep gamma ray observations? What do we do?
Yeah, I would definitely look into Fermi data set. So yeah, we were kind of bouncing around ideas. I haven't really explored, and I haven't mentioned it even here yet, but our solutions are perfectly happy with a point-like object, so like a very massive dark black hole. So one possible way to test that would be, if it's supposedly in a binary, to look at it in X-ray if there's like some signature of that. There is a very exciting proposal from the NYU group to kind of trace a massive object through the halo from its kind of from basically the wake it forms, like in the nearby like stars it passes by. So I suspect this is sort of like at the level of probably 10 years of Gaia, the precision in proper motion that you would need to do that, but that would be a way to identify a truly dark thing. And perhaps this is a possible venue for this sort of studies, because we would not only have the present day location, but also prediction of what the total orbit should be. So I think it would be easier to search for those sorts of signatures if we kind of know where to look for them than rather in blind. Yeah.
So what constraints on the mass of the perturbers can you set?
Yeah.
You showed that they might be globular clusters, but could they be more massive or less massive?
Yeah. So here is a plot I skipped in the interest of time. So the gray box shows models that we deemed are likely. We don't really have a very good likelihood at the moment, so I didn't want to overinterpret this. So I said like anything within this box is plausible. And so the mass is on the y-axis and the size of the perturber is on the x-axis, and the points are some of the known objects in the Milky Way, or rather all that have measured these properties. So most of the globular clusters are shown as triangles. Of dwarf galaxies, only 50% have determined both the mass and the size, so they are shown in squares. And then for comparison, I also show where the kind of outer disk molecular clouds would lie. So the spread that we find would be between 10 to the 8 and a few times 10 to the 5 solar masses size. And as I mentioned, like in mass, and the sizes can go basically to point mass. And here's like a size of 20 to 30 parsecs. And just for comparison, here is where we expect the lambda CDM subhalos to be, and this is a very small overlap.
So you didn't mention the Magellanic stream. How do these compare to the Magellanic stream in gas content and dust?
So I checked the orbit of the LMC itself, and that didn't come very close to the GD1 stream as none of the other dwarf galaxies. So it was at a
But I'm wondering,
yeah.
you know, the Magellanic Stream is a really bright object in 21 centimeter and has considerable amounts of dust in it as well. And so I'm wondering if these streams also have gas and dust in them, or
Oh, these streams. No, those are the globular cluster only. So they only really have stars. Even the disrupted dwarf galaxies. Yeah, we only detected in the stars. It is possible that the Magellanic Stream might be affecting, and we know we see a lot of evidence that Magellanic Stream is affecting like dynamics in the whole galaxy, and appears to be kind of the barycenter of the Milky Way has been shifted due to the passage of the LMC. So we definitely want to look into in the future when we integrate all of these orbits, when calculating how close everything comes to each other, to include the LMC, but we haven't done that yet because we don't have those sorts of models yet. Yeah.
One last very brief question.
Yeah, great question. So I assume you haven't found any other perturbation features in any of the other streams, or have?
Well, it's so yeah, I haven't really given you a sense of the time scale. So all of what I've talked about has happened within the last 18 months. So we really have been busy with just following up this one object. So I looked into this other stream, Polymer 5, where we see some evidence of perturbation. And there is another stream that I quickly looked at in Gaia. Okay, so this is one of another called JLM, where we see another unusual structure, such that we thought it was initially a thin stream, but now you can see it over here, and here's the histogram. It looks like it has two components, a thin and a thick one, and the thin is offset from the thick one. So it's a little bit unclear what happened there. So I guess I would say that of the three streams that we have looked in detail, we saw unusual things in all three of them, not necessarily signs of dark matter subhalo passing by, but yeah. Yeah, it's a little bit too early. It's consistent with what you would expect in lambda CDM. Like people forecast the number of encounters GD1 should have had, and it was just like a 1 plus or minus 1. So yeah, we're right there.
Okay, let's thank Anna again.
There's no way you can get a black hole perturber because in this mass range, they all sit in dense star clusters, and if it skips, it will drag a part of a cluster with it.
So you would see it?
So you wouldn't see just a 10 to the 7 black hole with a star orbiting it, a single star. It will be a cluster.
Thank you.
I had a technical question, which confused me. Many of your plots, you have gray circles and black circles. And I didn't understand what was the distinguishing characteristic